Okay, am I coming in? Yep. Well, this is going to be a real gear change here, okay? So get ready. And I'm going to try something on you, too, so you have to pay attention a little bit. I want to start off with telling you stuff about the space station. A lot of people don't know what's going on, because stuff's going on there all the time. And then tell you what PSU has got going on the space station. And I will probably annoy you a little bit by plowing through this stuff because they gave me a little grace on the time. So I want to show you some recent results of experiments that we perform at PSU in a thing called a drop tower just across the street. So if I can get to that, then I can show you what I think are some entertaining science, both discoveries and results that we actually use in our research. So this is the space station. It's been up in orbit for over a decade now. It's a giant-sized thing. Quite an achievement. It's the size of a football field. It's traveling over 17,000 miles per hour. It weighs 400 tons, a little over that, and it's doing all kinds of things. People kind of lost touch with it when they thought the shuttle, when the shuttle program stopped sending resupply missions. Actually, the shuttle built most of it, but it's continuing to function. I just provide a few slides of it to show you what it's like. This is a closer image of it, and even closer image. And even though it's going so fast, it's only 250 miles or so off the surface, there's nothing aerodynamic about it. Okay? Okay, they are doing all kinds of things up there. So since it started, they've done over 1,500 or so investigations up there. There are experiments going on inside, outside, building the thing, learning to live and work in space, as well as projecting down towards the ground. And I'll just highlight just a few of those just to give you an idea. They're doing material science experiments, fluids experiments, biomedical experiments. They're doing technology demonstrations. There's a commercial entity to it, a national laboratory entity to it. They do student outreach that's touched millions of kids and stuff like that. This is an example of an image of Chris Cassidy, one of the astronauts, doing a combustion experiment. I think we've seen many of these. These are very cool experiments. This is just to give you an idea of how gravity affects certain things. So your normal day life is totally messed up if gravity's gone. Nothing, in fact, that works on the ground will really work there in general, especially if there are fluids involved, and combustion is certainly fluids, okay? So you're used to this candle, but in low G, the same candle burns spherical, it burns cold, it goes out when it should burn, it burns when it should go out like this. And we got to learn those things just for fire safety on board, but it's also very interesting just fundamentally outright about all the stuff that they're burning up there. They burn paper and plastic, they burn droplets in free suspension, so it's really, really neat to see this stuff. The body undergoes all this change, and you know that the bones become fragile and things like that. They're doing all kinds of experiments like that because if we're going to go long-term missions, we got to solve all these problems, and the space station is the place to do that. So the astronauts they're getting poked and prodded all the time. And this is an experiment that actually is a test on all the liquids reorient in low gravity. Your head puffs up like a balloon a little bit and puts all kinds of pressure on your face. Makes you look younger, but it also puts pressure on your eyes and you lose your vision a little bit. And some of the astronauts have mentioned that, so they're doing studies like that. They're doing lots of stuff like that. There's all kinds of stuff on the outside. So this is called the AMS. It's a device that's looking into deep space. They're looking at dark matter, dark energy kind of thing. The first time I saw a presentation on it, they determined the concentrations of all the periodic table of elements, in deep space. Quite an instrument, huge instrument. A single shuttle flight was necessary to take that up. Here's another picture of the space station. This is the Japanese module right here. They have a bunch of items on a pallet outside exposed to space, looking at engineering materials. They also have a device on it called MAXI. It's an X-ray something-orometer, and they're looking at, they do a full field thing, and they actually helped identify a black hole that ate a star just a few years ago. Okay, so space station has stuff that's pointing out. It's got research that's going on inside, and they're doing all kinds of stuff. So the shuttle isn't flying anymore to the space station, but a bunch of spacecraft are. This is the Soyuz module that's bringing people back and forth, but the Europeans and the Japanese and the US commercial side is now sending stuff to space. I couldn't find it in time, but I had a picture, with all like 4 or 5 spacecraft parked at the space station. Quite an image. This is SpaceX. So SpaceX is one of the companies that's doing it. Here's the Dragon capsule being captured by the robotic arm and then birthed into the space station, and it has a bunch of all this stuff in there. Boeing and Orbital and SpaceX are all going. It looks like they're all going to a station. So it's going to be we're in a neat era here of space travel. But of course, images to the ground are just killer. So what's going on there is critical to NASA's future in space. In fact, commercial stuff in space. What they learn on the space station is critical to that. But they're also applying this stuff to the ground, and then the images to the ground are just great. And now you can actually see some of these on the web. There's live HD downlink to the web, and you can Google that and find that yourself. But the images are stunning, and they're arresting. When you're trying to do your experiments, and this is the kind of stuff that's circulating underneath, it's pretty impressive. There's Cape Cod there. You see Massachusetts, Rhode Island, Connecticut, Long Island all in one shot, so the world ain't too big. And you can see that atmosphere. That ain't too big either. When the astronauts come back, they're all kind of struck with this feeling like, wow, that place is finite. But keep flying around it, and you actually feel like, wow, that place is huge. So we got both feelings going on. Some images I just love, and I wanted to show you this one I love. This is the Great Sand Dunes National Monument in Colorado. It looks like the place in your kitchen where all the dust accumulates. The sand blows across the thing and is caught by the mountains and piles up. There are almost 1,000-foot sand dunes there. Go there. It's a beautiful place. But what a cool image of it. So they take stunning images. And sometimes they see volcanic eruptions and storms and stuff that aren't detected anywhere because no one's over that location. This is an island off of just north of Japan and off the coast of Russia. All the action you see here, from this exclusion zone of the clouds to avalanches to this whole thing. It's just great. I just love this stuff. But this is what we actually do. So PSU has had experiments up there for 3 to 5 years maybe or so. We have a variety of them. We have robotic ones that the students command from the ground. We send hundreds of thousands of commands in 24/7 operations from a room over there, in the engineering building. We also have these handheld experiments. And I'm just going to talk about those. We have 11 of these test vessels, and this is Joe Akaba, one of the astronauts, and Sunita Williams is filming her. She came and talked to us after her flight. And we do these bizarre experiments, and previous speaker said stuff about being weird and stuff like this. I wouldn't say weird. Some of these things seem a little dumb, but it's going to be maybe too hard to describe what we're actually doing to this group, but I'll take a shot at it. But he's just chilling out, doing the experiment, and we're talking to him from the ground. So we have students in our program talking to astronauts while they're performing the experiment. We're all nervous. We're strung out on caffeine. It's midnight. It's usually because it's on a different time shift. And so, but we're also very excited about the data coming down because we can't wait to prove our theories out and things like that. So this is the science. Do I really care to describe it to you? I don't know. We are studying capillary stuff. So this is like critical geometric wetting. This is passive capillary migration. This is passive bubble separation. And this is just bubble nightmare kind of stuff. Believe it or not, bubbles are very critical. You get a bubble in your line, you shut off the primary oxygen system on the space station. The liquid reorients in the toilet. The urine can't be collected. Astronauts die, right? The toilet fails on the way to Mars. The astronauts die. So liquids and bubbles and stuff really matter. It's going to be hard to convey that in this kind of setting, but so let me just pass on it for a time. So let me tell you, in the process of doing this stuff, we meet astronauts. We get to know them a little bit, and I wanted to highlight this guy. This is Mike Hopkins. They called him Hopper, but we could never because we just couldn't do that. He's just a buff all-star, and he conducted our experiment more than any other astronaut. Innovated different ways to perform the experiment, took thousands of still images like this, really enhanced our science. But we like him mostly, well, that's enough. But he also trained 2 other astronauts while he was up there on how to function the experiment. Our students trained him in Houston, but these guys went up later, they got onboard training from him, and so they doubled the amount of science they got. This is Rick Mastracchio, and that back there is Japanese astronaut Koichi Wakata. He actually became the first Japanese commander of the space station. Both of those guys performed the experiment so well, and we got to communicate with them and learn about them too in the process. This is a homegrown astronaut. This is Don Pettit. He hails from Oregon, but he's more like from another planet, really, because he's like us in lots of ways, and so we made a great connection. That's him drinking water from his fingers. Okay, he's the one who took images, these time-lapse images of the Earth that show all this action: thunderstorms underneath, cities streaming underneath, the corona or the lights or whatever those are, the stars rotating back behind. So he did a lot of things, and when he came down from the space station, I think he'd taken over half of the images up there, like millions as far as I know. Okay, so we hit it off, and he did some other experiments. This one actually went on NPR. It's an edible experiment, and it was aided by students in our labs. So these are candy corns, but they had a special coating on them to make them do this stuff, okay? So it's not just candy corn. So he built up this structure from this, and you withdraw a little bit of liquid, and it becomes this rigid sphere, and when he was done, he ate it. Okay, so I show you that. He also complained, that was an edible one. Here's a drinkable one. He also complained about sucking liquids from a straw. That's what they do. So they're called drink bags, and he just couldn't bear that. You can't smell it. You can't, he felt immature. He mentioned that. We sent him an email and said, hey, if you could make a container with that kind of shape, you could drink normally. And we didn't really mean that, but he found stuff and made it. And he made that device. Then he would make toast with friends, and they would drink normally, and so he'd drink his coffee that way. So this got a lot of action on both YouTube and on the web. And what you see here is you see that capillary forces in that interior corner are driving the fluid as if it was draining by gravity. So you replace the role of gravity with the effects of surface tension, and that's what we're doing. So what's the next slide? I don't know what the next slide is. Oh yeah. Okay. So here's this. Here's this drinking. So it looks like gravity's at work, but it's not. So it's not real drinking. It just gives you the sense that it is. The thing is cool about it. His nose is right over it, so he can smell the coffee. You got to smell it. You plug your nose and drink coffee. It's like, I don't know, orange juice. I don't know. Okay. So let's take a break now. This has really been a difficult subject. I know science is hard for everybody. Okay. And let's talk about this, okay? So I'm going to call this the math break. And this could be really wrong to do. But I want to show you something. And I want to show it to you. I don't want to tell you it. I'm going to show you. So you're going to get it right here. It's going to take about a minute and maybe 20 seconds, maybe 10 seconds. But let me show you what is done here. This is just coffee, but this is what we do. That there is a schematic of the flow along this corner. Get ready. Okay, here's a tip. Here's a tip. Just kind of watch. Don't listen. So I'm going to speak, but it's going to be like elevator music, right? That's the flow. Here it goes. Ready? These are the Navier-Stokes equations. There's 27 terms. 3 equations. They balance momentum along this flow. Okay? It's a nonlinear equation, never been solved, ever. Here are the boundary conditions that apply to it. They're very complicated. Some of them have physical quantities that we don't even understand in terms of physics. If the flow is slender, there's predominantly one direction of flow. So this equation is small, so we can ignore it. It's small, not zero. Same is true for this equation. So primarily, the most forces must balance along the z. That's this one. If gravity is small, which it is in space, if the flow is slender, that's true. And if the flow is really slender, then inertia is completely eliminated by the fact that this is pretty much a long, slender, one-dimensional flow. If that's true, only these terms matter. This is the capillary pressure, and these are viscous terms, solved in this cross-sectional domain. If I apply the no-slip condition here, it simplifies, and if the flow is slender, I get this great simplification of a nonlinear partial differential boundary condition that breaks down into simply the contact angle condition. If I apply those two to this equation, I can integrate this equation twice, solve for the velocity, take that velocity field in this domain, integrate it twice, get the average value. If I get the average value, I can calculate the volumetric flow balance here, which gives me this transient term for the mass conservation. If I then take this average velocity, substitute in that equation, and then recognize that this cross-sectional area can be expressed in terms of the height of the meniscus squared times this dimensionless geometric function. I can substitute that in and get this nonlinear second-order partial differential equation for the evolution of this surface along this edge in time. Got it? Okay? Okay. We're 1/3 of the way. No, two-thirds. So let's apply that to the astronaut coffee cup. Ready? Okay, if I define the amount of volume that comes out into his mouth as Q, and I identify the location of the bulk meniscus as it recedes into the cup as Z2, I identify a boundary condition here with something we call Kunkes fin theory. If I then take that equation that I just derived on the previous slide, I solve it for the free surface there, I can actually compute the drain rate into his mouth. It's a function of this thing, Z2. I apply then another boundary condition. Here at this boundary condition, I get a differential equation there that I can integrate and get this value for Z2, which I substitute in there, get the flow rate. Now I'm done. Okay, that's it. All of that stuff to get these things, and this is what engineers want. We want to be able to specify what the heck is going on as a function of all the junk that's in the problem. So this is the drain rate, but this is the drain rate, how much you can take in. It tells you that this cup can develop that much flow rate and put that into your mouth. It's a function of everything we care about. the surface tension, the wetting characteristics, the viscosity, the size of the container, the shape of the container, the interior corner, everything in there, even time. And we get this cool power law behavior and all this stuff. This is what you want. It's just coffee. Okay, this is the comparison. There's the data. Those are data points from drain rates, and there's the theory right there, right on top of it. So if you want to drink coffee on Mars, or deep space, or in drop towers or whatever, this is the equation to use. Okay? Okay? But we're doing this on all of our experiments, all of them. And we're just accumulating one solution after another, and gaining all of this ability to now use the math to predict systems that don't exist yet, so that they will function completely in space. So it's a highly math-driven engineering field, because you only get one chance in space, and it's an expensive chance, right? The cost might be going down, but it's still pretty expensive. Okay, so that was coffee. Now, that's close to Portland's heart, right? Coffee. It's a subject that, so it's not hard to get people interested in coffee. So what's the next step? Now, okay, let me say, before I do that, let's just say we want to use these methods to reassess all fluid systems on spacecraft. We're talking about the toilet. We're talking about water processing, the whole thing, from drinking to water recycling, condensing heat exchangers, coolants, liquid propellants, plant and animal habitats, biological systems, food. It's a big list. Okay, and what we're trying to do is use surface tension and this mathematics, this geometry, to solve these problems to make systems work passively, no moving parts, no electrical interfaces. We think this is the future. Okay, so but like I said, we need another demonstration. We've already done coffee. What could we do next? And let me say, we could work with espresso next, right? Espresso. So coffee's one thing. Espresso is also probably dear to a lot of Portlanders too. So we designed this cup. So that other thing was designed in space. They actually sent a 3D printer to the space station too, but we 3D printed this one on the ground. So we use our math to come up with this shape. And then we 3D print it, and we make it. So I have one of these things here. There's actually two versions. There's the transparent one. This transparent one, you can see this afterwards if you want to. The transparent one's going to space. We actually have 6 going to space. And then the 1G version too, if you're into that. Okay, so why? Why espresso? Check it out. So here's the cup getting filled with espresso. So this is not coffee. I mean, not simple coffee. This is a very complex drink. And there's so much gravity-related phenomena going on in here, it's just too cool to pass up. So we have all these bubbles are actually carbon dioxide. They're clinging to the wall here. They're rising to the surface. They're forming what's called a crema. There's different layers in the crema. You can see the crema is already wicking along the interior corner. There's condensate on the top that's driven also by a combination of gravity and temperature gradient. So this is actually a gravity nightmare. Take gravity out, what's going to happen? Well, coincidence, the Italians are sending up an espresso machine to the space station. It's a combination of Argotec and Lavazza. Lavazza is a primary espresso hardware company in Italy. And they go to do this, and they're going to put it in a bag, and no one's ever going to see all this science going on. But we're nerdy, right? So we want to see it. And so we say, put it in the cup and watch all this action. It's not going to be anything like you would expect. Is the crema going to be there? Probably not. Is it going to be distributed? Probably. Is it going to smell different? Yes. Is it going to feel different? Yes. Is it going to orient in there differently? Yes. The crema is this oily emulsion of all different kinds of things, so it's a really complex fluid, and it won't behave like they think it's going to behave. Anyway, when the cameras are rolling on this transparent thing, you're going to get a bunch of science in it. You're going to get a fun thing, and you're drinking and having fun, but at the same time, this is publishable science for us, Okay, so let me show you some drop tower results. And so this is a cup in the drop tower. Now, I don't care if you don't understand what a drop tower is. This is what happens. So the surface tension and wetting forces and the mostly important, the shape of the cup, drags the liquid around like this, so the astronaut comes over, makes a lip connection with the top of there, and it just will go in. Okay, that's without the crema. So we took the espresso, we swept off the crema, and here's a numerical simulation of that same process. We can take our geometry, port it in, and calculate it. So that's the drain, so it's going to be great. We're totally confident. But watch this though. Here's the crema in there, and this is a drop tower experiment. So it's in low gravity. It's in 1 gravity, all of a sudden gravity's turned off. You get this wetting up the corner, which we want to see, but you get no action here. The crema serves like a lid and just puts a cap on it. We believe that it'll flow, but it'll take a long time to flow. Your coffee will be long cold before that thing moves, you know. So it looks like we can't even test this on the ground. The crema interferes with the science. Okay, but so let me change gears in my own talk and start talking about a drop tower. What the heck just happened? Gravity was there, and then it was gone. So what happens? So at PSU, we have this facility. It's called a drop tower, and in that, we do work that supports our space flights, our space experiments. It's a unique facility because it's safe, and it's accessible by students. We even have summer high school students working in there. We have Drew Woolman, one of our Ph.D. students, is approaching 1,000 drops in this facility. So it's a low-cost, low barrier to entry thing, and you can use trial and error in it. I heard our previous speaker say you could fail, and you can. Whereas normally, if it's $1,000 a drop or something like that, you don't want to fail. Here, it's just your time, and you can pump them out really quickly. We can do 100 drops a day in this facility. So this is Brentley, and he's hooking this up thing for a drop. This is the 5th floor of the engineering building. It falls 6 stories. Most of it's been developed and designed by students. This thing falls right along the central staircase of the lobby. So there are some people that get pretty startled when they're looking at their cell phones, and this refrigerator comes by at 55 miles per hour. Okay? It falls into a permanent magnet field at the bottom that sets up eddy currents and decelerates it. So again, it's passive design, can't fail from electrical shutoff or anything like this. We can do lots of drops, turn them around quickly, and we work with other universities and companies on this, but mostly ourselves. We just have a flood of ideas, and we can be busy forever in here. When it's dropping, people gather around. Sometimes they clap. When we're doing tons of drops, they could give a rat. They're in there studying, and this thing comes flying by over and over again. Okay, and that's how it goes. So what I want to do is just give you an idea of what it's really like to be in our group and show you a bunch of dumb stuff but behind this all, though, is just like the coffee cup, is the science that does it. I'm not going to show you that stuff, but I want you to know it's behind it. So here's an example of how you won't understand anything about what happens when gravity is gone. So that is a styrofoam ball. It's floating on a liquid surface. Gravity is there. The whole concept of floating doesn't exist in space, right? There's no buoyancy, so nothing rises. Heat doesn't rise, right? Light things don't, okay? So what's going to happen? I'll wait a little longer. What's going to happen? Gravity's going to be turned off. What's going to happen? So the ball was a styrofoam ball. It just got completely sucked in. And this would be true of you, too. If there was a giant sphere of liquid right here and you tuck your hand to it, you're going inside. Okay, unless you struggle to get away, you're going inside. You could also change the properties of this sphere, and you could make it shoot off of that liquid surface. Okay, so we do one experiment after another that investigate things like this. This is capillary rise in a tube. On Earth, it just rises to a certain level and stops, right? But in space, it goes forever. If gravity is 0, you can have capillary flows that just go forever. So you can drain huge tanks, and things like that with just a little tube. If you put a little nozzle in that tube, the capillary force is enough to shoot itself out. Now, to people in the field to think about, hey, how could the liquid generate enough to shoot itself out? I mean, that was a trip for some people to take. Hey, what happened there? We sent an email to Don Pettit in space, and he did this on the space station, ejected a droplet 2 billion times bigger than what we could do on Earth. So these are giant-sized droplets can be ejected this way. He built that on Earth, too. You can make a bunch of different nozzle types to get all kinds of different responses. Single drops, double drops, quads, transient jets, all kinds of things. Now, so we're interested in drops and bubbles in space. Now we have methods of creating them with no moving parts. Just put them in the tower, drop them, bang, you got it. You got what you need. So then we start doing all kinds of things with them. This is a 3D printed base with 100 different jets, and they shoot out some 400, 500 droplets there. And now we can watch massive droplet interactions, acoustic fields, magnetic fields, all kinds of things to control that. Here we're looking at impacts against walls. Not all of them hit, and they bounce and scatter and stuff like that. You can make walls here that absorb them all. So, right, if you have droplets of urine in your toilet, you don't want them getting back into the air stream and back into the cabin. You'd like to get them all out of the flow. Whoops. Okay, so those are drops being shot. You can also look at puddles. So this is a puddle. So what happens in low gravity when you take away G? Remember, this is all in the drop tower. It jumps off. So this is what's called an ultra-hydrophobic surface, And it's made also by 3D print or 3D work, and then it's coated with a non-wetting material. But it doesn't like that surface. It tries to form a sphere and shoots itself off. Here's a giant-sized one. This is 10 ounces. This is your coffee spilled on the ground. This is massive. So this is 1,000,000 times bigger than anything you could see on the ground. And so, but this kind of stuff happens in space. In space, you have tons of liquid fuel in a tank, for instance. So we're getting closer to that kind of thing. Then you just can start goofing around. But if you can do these things passively with no moving parts, you have all kinds of capability to study other systems. No purpose for this at all. Okay, now we're using the shooter to do science. So now we're using this whole process of ejection to shoot a drop at the surface and watch this impact. This is a surface hitting this thing at room temperature. Okay, so it's room temperature. That's about a 2 milliliter drop, way bigger. It's 1,000 times bigger than a raindrop, for instance. Let's go to this next one. So watch this. So now we're going to heat this upper plate. We've heated that plate now, and now you impact, and you have this. So this isn't these are vapor bubbles that are bursting at the top, but they're ejecting all those drops. So the drop doesn't leave because of heat transfer to it. It's leaving because it's just shattering itself and losing its mass that way. Increase the temperature even more, and you get this. It doesn't even wet the surface. It's called the Leidenfrost point. It doesn't even wet and bounces off. So it bounces off this because it's too hot and forms a vapor layer and it can't touch it. This one, it bounces off because it doesn't wet it. So there's different ways to do this kind of thing. Once you learn how to do this, you can do it for all different kinds of things. You can determine when it happens and when it doesn't. And these limits are all determined mathematically. And then these become our design tools for how we make systems. You can control the rate at which things are ejected. So different surface textures and stuff will shoot at different things. You can get a mathematical expression for that. Then you can do other stuff. Do you want to see that again? Okay, you're invited anytime for a free tour, so stop in. It's across the street in the engineering things. I'm done. Okay, those are my acknowledgments. Thank you.